I've been kicking rocks for 67 years and my feet hurt. The other day, my wife came in and said, why don't you go find a big rock and crawl under it? And I said, I will if I can find one that I'm interested in. Anyway, it's been a long road and appreciate you guys showing up for an old fart like me, but anyway, let's see what we can do. I wanted to point out one of my not superiors, one of my teammates, Jason Price. There he is. Work for Jason, I wouldn't be doing all this work when I should be in an old folks home, but thanks, Jason, for keeping me going. Yeah. All right. What we're gonna do tonight, I told, somebody came up to me last week and said, what are you gonna talk on? I said, cracks and rocks. And they said, you gotta be kidding. Gotta be kidding. I mean, what can you do with a crack and a rock? Anyway, what I'm gonna try to show tonight is that those things are amazingly illustrative of a lot of things that can go on. I mean, we don't know when you see a set of, I think the first time I was really amazed by the character of these joints was when I was working at Cuesta back in the 60s. And I saw the very unusual fracture patterns that were, some were related or controlled and some not. And ever since that, I got hooked on looking at plutons. Because the nice thing about structure in plutons is you can date the structure. Because if you know the age of the pluton, you're pretty close to the age of the breakage of that pluton. And so there's been a lot of kind of revelationary work in interpreting the stress patterns in these plutons to different applied subjects. And we'll start with what are we going to start with? You know? Okay, you're in deep trouble. Anyway, let me press the buttons and see what is going.
What's a senior exploration consultant?
My button to my post. Get started.
John, there's a Spanish word for that.
Oh, I see.
BGF. That's a big old fork.
Okay.
Sort of.
Yeah, we're going to look at different applications for cracks in rocks and what they tell us that we didn't know before. There are rocks like these. That's where randomly I call them unsystematic joints. There's a recent lava flow in Peru. You can see how curve planar and irregular they are. There's a big chunk of granite in the front range and very poorly fractured, right? And this is what I call systematic joints, where they all are going the same direction. These are in a mineralized area in Arizona, and each of those fractures going in there are parallel, are mineralized with iron and some degree of copper oxides. Way back when, Hodgson in 1961 recognized there were two types of joining in rocks. One was systematic and one was cross joints. And then Price, where's Price? Oh yeah, there he is. Price and Rehrig redefined that a little bit more and said that the systematic ones are these straight line things. They're parallel and they contain mineralization, whereas the J2s are definitely post mineral and barren. Here's an example from Copper Creek, Arizona, where you can see the straight parallel breaks are the systematic J1s. They are mineralized with tourmaline. And on this slide, do I have a pointer here? Yeah. They're mineralized with tourmaline here. And these cross joints are completely different character. They're not straight, they're irregular, they're curviplanar, they're short, and they're discontinuous. There's another example in Jamestown, Colorado, where the chick, which I need help again, I sort of help. This is a Jamestown where these J1 joints, these are these straight parallel mineralized structures, are trending east-northeast. And you look opposite 90 degrees and you see what J2 looks like. Doesn't look like J1 at all. It's completely a different character and it plays a different role in the breakage of plutons. Here's an example, I guess, from rock mechanics, where you can create parallel extensional joints in a compressive environment, but you have to use, sigma 1, sigma 3, sigma 2 to form these in the right relationship. But I want you to understand that this is all compressive. You can create these parallel joints by compression. There's another example of how you disseminate mineralization. This is why you have porphyry copper deposits. Because this sigma keeps breaking that rock parallel until you get lots of parallel fractures in the direction that is the least principal stress. Here's another shot of Copper Creek. You can see that these J1 joints were then immediately filled with hydrothermal material, this case being tourmaline. So these are the first breakage that occurs in that magma mass when it solidifies and becomes solid enough to break. There's an example in Copper Creek. How many of you have been to Copper Creek? Anybody here? Yeah, Copper Creek is a porphyry district for sure. Lots of breccias stuff, but the amazing thing is that the intrusive rocks in that pluton are just absolutely riddled with these parallel mineralized joints bearing copper. This is an amazing slide because this is a silver bell over here on the left, and these are the benches there in Silver Bell in the quartz sericite zone. You can see that there's a parallelism going on here, but when you get down really close, look at these veins. Those are quartz veins at the phyllic coloration, and you tell me how you can get a rock that will split that evenly and that close together and inject quartz without compression. Can't do it. These are other examples of J1 type fractures in different places. Now, the idea here was originally, at least to my knowledge, was originally proposed by, who was that? Price, yeah, just by Price in the 1960s. And this is how it goes. First of all, you're gonna get these first breaks that are mineralized because you've got sigma 2 or you've got sigma 1 vertical. It's, in other words, it's down at least a couple of kilometers deep. And then you've got a compression, a lateral compression that exceeds this axis, and you keep breaking these things and filling them with mineralization. Then there comes a time when the sigma, these unsystematic joints start to form, and they are amazingly nearly perpendicular to the J1s. These are J2s, we call them J2s. They're irregular, they're short, they have coarse surfaces, and they're definitely a release type of a fracture. And it's definitely way different than in the mineralization era. And then, where am I here in this house? Anyway, that lower, that one, the compressional elastic strain, when this sigma starts breaking these rocks in extension, they compress the rocks. Those rocks are taking on a strain, intergranular strain that represents this diagram right there. And then after uplift or relaxation, that rock wants to expand. I remember one time we took a drill core and we put it in a piece of laramide granite. This was here at the U of A. And we cored that thing. And then we measured the axes on the circle. And by God, in a week or two, we started to see that thing start to become an ellipse. It started relaxing that intergranular compression. And that's a key factor in a lot of this application work. We'll look at the exploration here for a bit. And this is probably some old slides. Some of you may have seen them before. If you look at the Silver Bell area here, you see that you've got the main veins, laramide system are all just cracking out here, big as you please, in the east-northeast direction, until they meet this structure right here, which is Courtright Richards major structure, which is a west-northwest bearing, strike slip fault, an old one. Things start to change when you get in there, develop this a little more. But right now, what I want to emphasize is in all these districts, here's Morenci, for example. You see the intrusers are lined along the northeast direction, as are the veins. And here at Esperanza, okay, let me go back. Here at Esperanza, we have the same kind of a pattern. We see all the extensional structure going northeast, the laramide, but then you come in here in the area of Sierra and the pits, And you see that there's a west-northwest control that is mastering things and overcoming this stress field. And we'll look at the effects of this west-northwest influence in a minute. This is the Lawrenceburg vein map of Hydrick and Tiddly. And you can see how they are unidirectional pretty much, except up in here, they get these faults here that have disturbed things, have their own influence on mineralization. But when you put all the data together, as shown in these diagrams, you find out that during the Laramide, from 50 to 70 million, more or less, the stress pattern was regional and it was affecting all the porphyries. So we had to say to ourselves, well, geez, if we want to find porphyries, we've got to find northeast conduits, tectonic conduits. That's part of the story. And then we look at the regional aspect of the stress for the whole state of whole Southwest, which would incorporate quite a few porphyry deposits that are south of the plateau. And we see a sigma 1 as being the overriding structural control. But then there's another culprit hiding in the woods. And that is these long, old west-northwest faults that have been called heck, what do they call it?
It's Texas Lebanon.
Huh?
Yeah, lineaments, I guess.
Yeah. All right. But you can see how they, some authors like Keith and Swan has proposed these faults going all the way to Texas lineament, yeah. And all the way from California. On a more detailed scale, you see the individual faults that have caused transversional variations here in the veining and these other structures, but it definitely had a big control on structure here in this mountain range. Same here. My own wizardry, if you call it that, is that I've defined a bunch of these faults myself. They're probably too much similar to what Keith is doing. And so if we put this stress system in together, we have two major influences on mineralization. One is the extensional northeast, east-northeast, east-west opening caused by the compression from the plate tectonics, Aileron underneath the North American plate. And so you would have these as extensional corridors, but then when you cross these big west-northwest faults, you have two structural controls going on at the same time. And that's the optimal place to look for porphyry coppers, is at those intersections of those two structures. And sort of to prove that, I plotted all the porphyries in their geographic order. And you can see that all these porphyries either pretty much line up either with these west-northwesters or the intersections of the northwesters with east-northeast extensional zones. And these I have mapped on the surface. Oops. These zones here of extension and diking and veining can be mapped in the field. And they form a huge corridor, if you will, of weakness in crust. And then when they meet these biggies here, you've got your porphyries located. So that's a good exploration model, actually. Now, another application for exploration would be that we have found that that these darn J1 joints that are mineralized, they get closer together as you get toward ore. This is an example that I took from the Tyrone district. You're only 1 kilometer from the pit. You can see how intense this repeated joining is. And all at this point, there is percolating alteration in the joints. Then when you get out about 2.5 kilometers from ore, you start seeing them spread out, become less dense. And then at 3 kilometers, you have to jump from one to another. So there seems to be an influence here on fluid pressures approaching the core porphyry district. Because with the fluid pressures acting with the extensional stress system, you can create those closer and closer together. That's a good exploration tool. You start seeing that those joints, a matter of centimeters across from each other. You better start looking for something good. All right, go into open pit structure kinematic analysis. The benefits here are establishing specific structural ore controls, determines the directions of potential ore extensions on the outside of the pit. You know, these deposits sometimes spread out a lot more than when the initial discovery was made. You'll have your high-grade centers, but yet they're structurally controlled, and most often they are elongated. And then it discovers which fracture sets are most detrimental or favorable to mine pit wall stability. This is a terrible picture. I know it's too deep, but this was taken of a wall mounting about 4 by 4. I couldn't find it in my mess in the basement. But this is a kinematic structural job that we did at Tokapala, Peru. And you can see how we did the structure along every kind of bench and outcrop that was available around the pit. Here is the corner, here is the main pit back in about 1997 or so. Notice that there is a large stress. There's a large fault. Again, one of these west-northwesters went through here called the Micalaco zone. And there's several more parallel ones in this region. We have areas here here's the extensional corridor. It's from east-west to northeast. And this would be the result of regional stress. Then we have areas in which you have a radial pattern almost shown, where you've got different things going on with respect to the center of the deposit. Then along these big fault zones, look how all the structures align parallel to that fault. So there are several things going on here at once. There's a regional effect. This is a complex effects of local structures, pre-existing structures. Now, this is It's an amazing photograph because this is in Peru on the north side of Tocopala. These are the east-northeast J1s, all mineralized. You turn 90 degrees to another bench, and this is the K2 fabric. It's just a disordered mess of open fractures that are dangerous if you put a wall in along that side. This is another one of these big maps. I couldn't locate it, but this is work we did at Yanacocha. And the interesting thing about Yanacocha, as opposed to Tocopala, was that Yanacocha is in a volcanic domain, high level. And Tocopala is in a pluton. Probably we're talking about a couple of kilometers difference in the sigma 1 compression between the two areas. And we realized that at Tocopala, there were similarities to, at Yanacocha, there were similarities to Tocopala in that there were these major shear zones that went through here. And then we had these regional northeast structures that represents the key structures for controlling mineralization. There's a lot more in here, but these are the stereo-nets of these areas here. This is stereo-nets of this northeast system here. Now, I ran across an interesting publication a number of years back. It said lab tests that showed deviations, stress deviations at points of resistance, discontinuities. And this is an example of, you have a major discontinuity here. These are the stress lines. And you can see that those stress lines are deflected inward toward this point of resistance. That has applied to the models that we've come up with in South America, where you get two kinds of deflection structures. You get transpressional joints, which are going northeast. Here's the regional stress pattern right here, effect from plate tectonics. Here are the faults. And when you get into these left lateral faults, you will turn those like this. You would turn those structures in almost perpendicular to the major structure. And that's what I think has caused the main ore breccia there at Tocopala to be northeast, whereas all the veins surrounding area, like Butte, are going east-northeast. So, looking at a couple of districts, you can see that the strike deflection becomes an important ore control. Here is the Silver Bell district. This is the major structure of Port Richard. And you see how it takes a bend. And at these corner points here at the bend, are where the pits are located. Both of these. Here's an example of Del Mar Gold District, where again you have this flexure in here, and you get controlled mineralization at that point. Because when you're doing this, you can open up some of these areas of deflectors. Good for mineralization. Another interesting thing about Silver Bell is that the mapping of Port Richard did a lot of vein mapping, and This is all these dark, short lines. And if you'll notice here, that the pits are right there where all the stuff is going north, northeast. And here, they're more east, northeast, but there are these deflections where this fault curves right there that creates a lot of open space for mineralization. This is the oxide pit here, and then the major structure passes more or less through here. But you see, these are controlled, these west-northwest structures are controlled by the major structure. That has a certain effect on parallelism. Then in here, where you cramp that down at that curve, you've created a transpressive environment. So the veins become north-northeast rather than in the regional stress field, which is east-northeast. Does that make any sense? Another thing that affects structure in these areas is major faults, structural lineaments that have on the joint veins and intrusions. Let's look at Caridad for a minute. Caridad is down in Sonora, Mexico, and you can see that there's some big faults going through there that are again west-northwest. And where those faults interact with the regional stress field, which is northeast, east-northeast, you can see they become transpressive going northward, or they'll become parallel with the fault itself. This is right in here is probably the direction of the major tectonic stress, east-northeast. Then here's a good example in Cuesta, New Mexico. This is I thank Tom Heidrich for this. This is the Rio Grande Rift right in here, or the Cuesta, not the Rio Grande Rift, but the Cuesta lineament that has taken all these tertiary structures that were initially in place in this north-northwest direction and turned them all around into east-northeast. That was one of the big taboos that I came across when I was doing my dissertation. Said, here's an east-northeast, that should be laramide. But yet Tocopala is a tertiary. Well, because there's a major flaw through here that reoriented everything and took from the regional stress field to a particular zone called a mineral lineament, I guess. Okay. All right, closing in on it here. Jason and I started looking at plutons in general and figured out that these plutons are strain gauges for regional stress. And so if they're strain gauges for regional stress, let's start in the Jurassic and work our way up to the Neogene and see what the J1 is doing in those plutons. Here's the late Jurassic plutons at Newfoundland, Utah, and this is this west-northwest breakage. And here also northwest breakage at Gold Hill, Utah. These are satellite images. We go to Sylvania, Nevada, Jurassic 159, 149 is, again, you see this direction exemplified in the breakage that, and what you can see best on satellite imagery is the J1 breakage because it's long, straight, and it's parallel, and it's hard to miss. Silver Zone Pass, it's the same, and at Delta Buttes, you've got the same pattern. So, what are we saying? were saying that in the Jurassic, there was a tectonic compression that was parallel to those faults. Now we go to the Laramide. We see instead of west-northwest, now we see east-northeast to east, almost east-west. Not only in Arizona, but also in Colorado. So that stress system goes through one heck of a lot of upper continental plate. Here is Laramide, example of Laramide. This is the Schultz stock. And here are the J1s, east-northeast. You see the J2s breaking orthogonal to it in a lot of places. Short, discontinuous. But these long J1s are, you can't miss them. Here's what they look like on a road cut. Okay, if we go a little younger, we'll talk about the mid-tertiary, from 40 to 30 million. Well, my God, they're not going east-west anymore. Now they're going north-northeast at Frisco Peak. And here in the Tectonic district, almost north-south to north 10 west, east. That's from 30, 32. This is a 31 MA. And even in Arizona, we could find a few 30s, very rarely. Most of them are Miocene, you know, are in the 20s or in the Laramide. But here at Goose Canyon, they have a KAR date of 31. It's probably a bit of a minimal date, so we're talking about the 30s here. And you can see the J1s forming right here and here, and these are mineralized. And then if we go up to Tectonic area, Swatch range, oh no, this is not Tectonic, it's Colorado. We see that the dikes are the 38 to 39 million year old dikes. They're going just flat ass at the north 10, 20 east. The veins here in the district here, Princeton, Batholith, are all northerly trending as well, again in the 30s. Now we go to the neogene and we cross over another strain boundary. This one being that things have changed from 30 to 40 to 30 to 20. They've rotated around into almost north-south, north-northwest extensional breakage, J1s. And then in the Newberry Mountains, Nevada, the Spirit Mountains, Nevada, you can see that these are less than 30 million years old, and they are going west, north-northwest. So when you put all that together, you see that there's an amazing rotation going on here between Jurassic, Laramide, mid-tertiary, and Neogene. 40, 50 degrees of counterclockwise rotation. Right, Jason? Maybe, yeah, maybe even more. Okay. Well, what's that telling you? If this is all the J1s are formed by plate tectonics forces over wide regional areas, there must be a connection between this revolving and the stress system. And thanks to a couple of very ingenious geologists, Greece, this gal, 1983, found a difference in the structure in the Rocky Mountain Range, the Colorado Plateau in both cases. And here we see You see all these uplifts going northerly trending by compression that is perpendicular right here. But then all of a sudden, you see them changing at a later date to uplifts that are 90 degrees from that. That would indicate north-south compression. And then she put a map out and said, how do you explain that north-south stress pattern and rotation? And this gal came up with an idea that I think is fairly unique, is that when you open the Arctic Ocean here, then the plate movement of the North American continent is northerly instead of east-west as it was in Paraguay. Now, the correlation here I thought was rather amazing. I got to tell you, there's been all sorts of tracking going on about the way the plates move. So you can get anything you like. I like this one because it agrees with our structure. You can see that that Jurdy in 1984 had this rotation going on from 60 to 10 million years, 80 to 10, all going north. The two models, the Arctic 1 model, this is Arctic 2 plate model. But according to this, that after about 30 million years, the whole stress pattern changed. Instead of going an east-west kind of a system, now we're talking about northerly system. Instead of wind up here, joints and veins and dikes are not randomly trending, like we used to call them stockworks. Now, mind you, there is stockworks. They're in breccias, you know, they have their own stress field. They break in every direction they want. We have the effect of older structures that deviate the stresses and the joints. But as a whole, these dikes are systematic. They're largely controlled by regional tectonic compression and owed to earth plate tectonic stresses, and are modified by major faults, crustal weakness zones, and extensional lineaments. These controls at optimal intersectional or linear locations create very favorable sites for the emplacement of porphyry copper mineralization. Knowledge of the joint types and their origins is useful for evaluating pit wall stabilities. I don't think I've spent enough time in that. So here's the deal. Instead of going back, I'll just say, if you compress those rocks, believe it or not, they develop an in situ strain. And then when you take away that compression, either by uplift or by mining, then they want to spread again. They want to work their way out. That's where you get into trouble in the pits and benches. Because if you've got a bench that's parallel with those late fractures, and you need low angle structures to go into them as well, you're gonna have danger in your benches. It also works well in designing the blast patterns to know which rocks are in this compressional mode, which ones are in the release mode. Yeah, then it's useful for evaluating pit wall stabilities, weaknesses, and can also be applied to predicting ore trends outside the pit boundaries. Once you find out once you find out what your opening system is, these porphyries, your J1s, then you can track that word out from the pit and extend your pits in northeast or east-west direction as well. Then the Stryker J1 joints and plutons of different epochs can track amazingly the interactions of the tectonics through time. So that's what I got.
There must
Can
be
you
some
come up and help
questions.
me with my ears? For questions? I think I can hear you.
Bill, I begin with, I just want to share how appreciative I am. You're sharing these insights from which incredible periods and observations. Along those lines, I want to ask the big picture. And the question behind it is whether, I know you work internationally, whether you've seen evidence for any structural sets that reflect the rotation of the earth. Simple as
I mean,
that.
due to this.
Due to the stress related to the rotation of the earth.
Well, as of yet, no, I have not. But I want to point out another thing that you failed to mention is that after Tom Heidrich and I did all that work in Arizona early on, got the laramide figured out. We went to Peru. God dang it, the Peru is the same controls. Plate tectonics along the coast. They have west-northwest major structures and east-northeast to east-west tensional structures. And it was a piece of cake to work on those deposits because amazingly it was the same tectonic control as we go around in North America. Going on.
So tectonics is more important than the stress regime associated with the rotation of the earth.
How's that?
So stress associated with plate movements appear to be more important than the stress regime set up by the
Yeah.
just a simple rotation of the
If you're
earth.
gonna do exploration or mining, you wanna find out where J1 was. Where the J1 fabric is, because that'll define your sigma 1. It'll define your mineralization alleys, and it will define the benches that will stand up, because those fractures are mineralized, they're glued together. Whereas there's perpendicular ones, they're the scary ones.
Thank you.
I found it very interesting that on your Colorado map, you showed a set of roughly north-south structures that were mid-tertiary. And that struck me because I was working around Freed and Gunnison in the last few years. Freed District, the Goldbrick District, and the St. Elmo District are all north-south main systems.
What age were that system?
I don't know, I guess they're tertiary now.
No, yeah. Yeah, we began to notice that even early in Arizona that, Tom and I saw the east-west of the porphyries, but then we saw the north, the opposite direction going on as well. And, but that was post-laramide. Doesn't really affect it, but then in the tertiary, that stress system went up 90 degrees, and this where south became instead of east-west. Yeah, you saw that too, huh?
Yeah, in the
Yeah,
field.
good, good. So I'm not lying, I got a witness here.
Actually, in San Juan, San Creed, Lataro, and other places, the mineralized veins are going northwest. They're not going north-south. And not only that, but the major mineralized structures, all of them, from the Silverton district to Creed to Lataro and other places in between, have right lateral offset on them. Or actually left lateral offset on them, which is interesting.
Help me there, Jason.
Which is, as I interpret that, as a response to the extension
Yeah, John, you've done
of
a
the
lot of
Western
work on
United
that.
States
Kind of
during
Mexico,
the
right?
Miocene,
Yeah,
which we know is But it's twice, 2 or 3 times as wide now as it was
Sure.
back in the Laramide.
And if you look at the veins in Mexico and Sonora,
You see the
they're not
same
east
thing.
west. They're big opening things, extension.
In Mexico, actually, the
Well,
Laramide veins, the Laramide mineralized veins go easterly, westerly, like your Laramide
Yeah,
vein.
yeah, it
And
continues like
the
that.
tertiary ones go northwest.
Yeah,
Voila.
yeah, good, John. Sure. Well, anyway, I didn't think when I was looking at the question in my dissertation that I'd get hooked on cracks and rocks. But God, it has it's been an interesting game, hasn't it, Jason? It is enlarged tremendously. Okay, that's the question. Yeah, sure.
John Sayles did a study a long time ago.
What's that say again?
John Sayles,
Yeah.
a PhD in data, and then published on it. He took and looked at the ancestral Rockies and the northern Rockies. They're all controlled. West, northwest, less slip faults.
Right.
And actually, that stuff goes all the way across the continent.
Well, it was you, Chuck, and your partner that defined, that said those west northwesters were so important.
Keith Kettner,
And they go back to the Precambrian age.
yeah, they're basin control.
Yeah, you're right. Mineral control too. So when you take those plates and you move them this way, you cause a deviation in the concentration in the opposite direction to give you your ore control. You put the two together, there's your targets.
Okay, if you have a joint fabric set up, let's say in the Laramide, doesn't that influence your joint patterns in, say, the neogene?
It's very patterned in way.
In the neogene, the younger.
The younger stuff,
Yeah,
only the big faults. The stress pattern does not get overridden. It's, you're saying, should the Laramide affect the tertiary? Right. Well, don't forget the Laramide is already done. That stress system is done.
but the joint pattern's still there,
Yeah,
okay? But isn't that joint pattern a fabric that's concentrated in whatever its directions are? And it's influencing the later joint set. That it could be, or later stress set, I should say.
yeah, it could well be. I do know that, when you get, how many of you know this Alabama Hills or the Sierra Nevadas there? Well, that's a Plutonous, Cretaceous evidently. And when you look at the satellite images of that Pluton, you find an amazing strike deflection from east-northeast along those west north, turns around. And it goes either two ways. It either turns parallel to the west northwesters, or it will become angular in a transtensional mode. And you can see the effect so beautifully in those outcrops there in the Alabama Hills. So previous structures do affect, they override. But then on the reverse thing, the reverse happens. Major structures control. Some places like in Cuesta, they control the whole damn thing. And that really stunned me, and if I repeat this, I was looking at Cuesta doing my dissertation, I said, oh shoot, here's a 22-year-old Molly deposit that is going northeast. And I said, that's crazy, because later I said, as I got to be dumber, I found out that it should be going north south. Then Tom gave me that big dike thing, and I saw how a lineman can just go like the same things. Want to say anything?
No, I don't think so. I just wanted to hear
No,
what you
no,
had to
it's
say.
just like-
Well. It's putting me on the spot. Bill and I met at San Javier, Sonora. I brought a piece of half board that I encourage you to look at. We did a structural study there at high level volcanic rocks. Probably not buried more than 1 to 2 kilometers depth ever. The joints there, some of them were systematic and some of them were not. They didn't quite behave like some tectonic fabric that Bill has shown you. Nevertheless, that kind of it kind of holds together just enough to be really intriguing. You're probably wondering what this younger guy is doing, kind of following up on these joints. Well, in part, what I would like to see is more work done on the magmatic fabric, the dikes, the veins, and the joints. Not so much focused on the joints. Maybe one of these days I will give a talk and I'll show you some of this other data, but if you imagine that you're going to go to all these plutonic sites, compile all that data, that's going to take quite a lot of time. And a shortcoming in geologic mapping is that you cannot dig out all of those various pieces from a geologic map. And so there are some shortcomings in our mapping that need to be addressed. There's some shortcomings in the way that we conceive of these fraction networks. I will say that the way they are modeled these days are as discrete fraction networks, DFNs. If you want to do any literature searching on this stuff, you need to look up DFN and not joints. So most recently, Bill and I presented at the GSA meeting in October. He gave the talk about the rotation of the vectors that he showed you here tonight. I do find that a very compelling idea, very intriguing. It's not clear during basin range extension what is providing the compressional stress in the north-south direction. I will say that is a standing question that I don't have an answer for. But nevertheless, the joints, for whatever reason, seem to hold together over a very wide region. So just as a reminder, we're talking about from southern Arizona, at least up here to the front range. And of course, begs the question, what is buried under the Colorado Plateau? What is the expression in the Colorado Plateau for some of the same sort of? So this is an ongoing avenue of research that requires a lot of field work. It requires digging into the literature. It requires some mapping that, to be honest, we haven't been doing. And just stay tuned. This is your career information.
Any other questions?
Yeah.
Okay, well, thank you. We would like to present you, Bill, with the certificate of appreciation. We're not done with you yet.
Another plaque.
Another plaque. And well, practically a.
What's that?
Chocolate.
It's better than on papers.
I think so.
Very good.